Negative 4za squared over a squared plus z squared squared. Anything else? A squared plus z squared, like this right here. There's one of them, right? And then there's two of them down there. So I can cancel one of them out and then cancel one and just be left with one of them. I can also reduce the 4 and the 2, right? So my new numerator is negative 2za squared over what's left on the bottom. A squared minus z squared times a squared plus z squared. Hey, isn't that a to the fourth minus z to the fourth? Right, like if I were to write x plus 2 times x minus 2, you would say that that's x squared minus 4, wouldn't you? That's a difference of squares factored over there in the top right. I'm just doing that here. I'm kind of saying like x minus 2, x plus 2, right? So it should be x squared plus 4. So that is a difference of squares factored. Do y'all agree or not? Now, if you would have just gotten it to here, you know, I wouldn't take off for that. I'm just pointing it out that, you know, that's probably what the book has. Questions, comments, concerns, gripes? Okay, let's try something else. Yes. Sure. Because 1/2 was being multiplied in front of a function. It was not 1/2 by itself. Like if I write 1/2 plus x and I say what's the derivative, you would say 0 plus 1, because the derivative of 1/2 is 0. But if I say what's the derivative of 1/2 times x, right, or 1/2 x, your answer would be 1/2. Because what you do is you carry the constant with you and you take derivative of x. That 1/2 was being multiplied times the natural log, so we carried it. Okay, I'm just picking another problem here. I'm going to just make one up. Okay, y equals 7 to the sine to the third of 5 to the x plus x. So what do you see happening here? Chain rule. What's the last thing happening? Anytime you want to try and figure out what's happening last, just imagine you plug a number in for x. So you would, if you plug in x, right, the first thing you would do is figure out everything in this parentheses, wouldn't you? Like, let's say I'm plugging in 2. You do 5 squared plus 2, wouldn't you? Then you would do what? After you figure out that number, you would do what? Take sine of that number, right? And then you would do what? Cube that number. And then what would you do? Take 7 and raise it to that answer, wouldn't you? That's the order of operations in doing that. So going backwards, the last thing happening was the 7 to a power, isn't it? 7 to junk. So we need to ask ourselves, what's the derivative of 7 to junk? So what's the derivative of a to the junk? a to the junk. So this will be 7 to the junk, right? Won't it just be itself? But then, times, very important here, ln of 7. And that takes care of the derivative of 7 to the junk. But then chain rule says you now need to multiply that by what? The derivative of the junk. So good. 3, because I'm taking care of the cube now, right? 3 sine squared of 5 to the x plus x. So now we've taken care of the derivative of something to the third power. Chain rule says keep going, times, now what was the next thing? The derivative of, we did the cubed, we haven't done the sine yet. What's derivative of sine of something? Cosine of it. Still chaining along here, times, finally, oops, I'm running out of room here. Times, now we're done with the sine, so inside, what's the derivative of, well, you have 5 to the x plus x, right? That's a sum, so you can do them separately. What's derivative of 5 to the x? 5 to the x. Isn't 5 to the x like a to the u? Times ln of 5 times 1, but you don't need to put that. Then plus what? 1. Okay, now I'm kind of out of room here. See, what happened here is the derivative of the 5 to the x. The derivative of that is this part right here. And then the derivative of x is that 1. So the derivative of 7 raised to the sine cubed of 5 to the x plus x is 7 raised to the sine cubed 5 to the x plus x times natural log 7 times 3 sine squared 5 to the x plus x times cosine of 5 to the x plus x times 5 to the x times natural log 5 plus 1. That's big time chain rule right there, right? There's a lot happening.
So the ln5 is from the a to the u.
That's from the formula for this. The derivative of a to the u is itself times natural log of a times u prime. Now the u prime is really just like the continuation of the chain rule, because your u prime may turn out to be another chain rule. But the natural log of a is just a constant that always needs to appear there. Okay? Very good question. Very good question. Let me illustrate this a different way. All right? Because we're about to head into this direction anyway. The derivative of x squared is what? 2x. So what happens was the 2 came down, we did x, we subtracted 1 from the power, we got 2x to the first power, right? That's because we were working with something that looked like this. Our variable raised to a number, right? Variable raised to a number, we get nx to the n minus 1. The important thing here is that this is our variable and this is a number, right? If it's the other way around, 2 to the x, all right? The derivative of this is not, okay, is not x to the 2 to the x minus 1. You don't bring the power down and subtract anymore. That is not the case. What you do is use the formula I gave you. It's 2 to the x. It's itself natural log 2. And that's using the fact that a to the x, the derivative of a to the x, is itself natural log a. Does that answer your question? And here we have the number, and here our variable is here. So you see in the top one, it's backwards than the bottom one. In the top one, your variable is the base, a number is the exponent. On the bottom one, your base is the number and your exponent is the variable. Totally different formulas for each of those cases. All right. I think the rest is just kind of fun for you to try and figure out. You're just going to have to play with these. And you get the gist of it, though? The homework assignment for that's pretty in-depth, so and there's a lot there. Now, we're going to get into something that's really, really nice. It's called logarithmic differentiation. Logarithmic differentiation. So I'd like to motivate this whole idea by an example. All right, like what the heck is this going to be? Let's start with this classic example right here. I'm still in 3.3. Okay? Logarithmic differentiation. Here's the problem. Find y prime. What do you notice is an issue here that we have? Yeah, there's two x's. See, if that was x squared, I'd be fine, right? It'd be 2x. If it was 2 to the x, I'd be fine, because then the derivative would be 2 to the x natural log 2. So I have ways of dealing with it when one of those is a number, right? Either the exponent or the base. But I have no way, up to this point, we have no way of dealing with it if your variable appears in both the base and the exponent, right? So notice variable, oops, your variable appears down here, and you have a variable also up here. And that's pretty much like, oh, what the hell do we do? Well, we do what's called logarithmic differentiation. And it uses the power of that property of logs that I put up on the board earlier, where you can pull the power out front. Remember that? Okay, the n came out in front. We're going to use that power of the log to figure out the derivative of this. So the first thing I'll do is I'm going to take the natural log on both sides of this equation. That's why they call it logarithmic differentiation, because you're going to do a derivative by using a logarithm. Logarithmic differentiation. So I started out with that equation on top, right? Y equals x to the x. And working with the equation, I can do the same thing to both sides of an equation, and it's still the same, right? It's like you have an equation x equals 2, you multiply both sides by 2, it stays the same. When you take log on both sides of an equation, it stays the same. So nothing has changed yet. What am I trying to get at again, though? I'm trying to find y prime, right? Okay, keep that in mind. I'm going to now, though, take that x and pop it out. So I'm using that property that if you have x, natural log of x to the n can pop out. All right? That's what I'm using. Very, very nice formula. Property of logs. So I'm treating that x like it was a power, right? And I'm pulling it out in front. Is that all right? We're okay with this? Now, don't I have an equation that has x's and y's in it? Right? I mean, I have an equation that has x's and y's. Can't I do this now? What was my little squiggly line representative of? Implicit differentiation. Implicit differentiation. Right? That's what the quiz we just did was over. So remember, I want dy dx, right? That's what I want. Y prime was dy dx. So look at the left side of that equation and very carefully tell me what the derivative of natural log of y is. So what's the derivative of natural log